Hello friends, from last few of our lectures we have been looking into this topic called as Simplex method. Now we have seen what the basic concepts were, we have seen how to solve a question based on maximizing and minimizing types. If you have not watched the previous videos, make sure that you go and watch the previous videos of Simplex method. The links to those videos is given down in the description box. Now in our today's session, which is going to be the last session, we are going to see some typical questions of Simplex method. So students, I welcome you all to this channel Pankaj Lade. Our today's discussion is going to be on some typical questions of Simplex method. So now I have written two questions here on the board and I'm going to discuss the two questions. Now what I want you to do is watch the previous videos how to solve Simplex method, understand the concepts for these two questions, and you apply those concepts of Simplex method that you have seen in the previous lectures to solve these two questions. Now in this lecture I am not going to take all the concepts here. I am not going to solve this problem completely. It is left to you to solve these two questions and get their answers. What I'll be doing is I'll be telling you what is different in these two questions. That is what we are going to see in this particular lecture. So this is our last lecture for Simplex method. Let's begin with the two questions. The first question that is given over here is solve the given LPP using Simplex method. The question is for maximizing. Now you already know that the very first thing that you should be checking for a given linear programming problem to be solved by Simplex method is your objective function must be of maximizing type, isn't it? The objective function is of maximizing type here. Further, there are three subjective functions given to us: 2x1 plus x2 less than or equal to 10, then there is 2x1 plus 5x2 less than or equal to 20, and 2x1 plus 3x2 less than or equal to 18. Three subjective functions are given and all of them are less than or equal to type. All of them have the right hand side non-negative, isn't it? That was our second rule. The right hand side of all the equations of all the subjective functions of all the inequations, the constants we can say, should always be non-negative, and all of the inequations should be of less than or equal to type. So that was the second condition. It is also satisfied, and all the all the decision variables given to us should be greater than or equal to 0. So now I can observe here the given linear programming problem is already satisfying all of my conditions, isn't it? That means I can straight away start with the Simplex table, and you know how to start with the Simplex table, isn't it? You have a basic variable, then you have to write coefficients of the decision variables. x1 and x2 is present over here. There are three inequations, so there will be three slack variables present over here: s1, s2 and s3, isn't it? Then you write your objective function with s1, s2 and s3 and so on. So you can complete the Simplex table. Now what different you have in this question is, isn't it? So far we are doing the same things that we have discussed in our previous lectures for Simplex method, isn't it? So there is nothing great about this problem, but you have to watch the question very carefully and very closely. What difference you are going to observe here? Let us check that. Now whenever we talk about the optimum solution, now you remember what an optimum solution is, isn't it? The problem is asked for maximizing. That means the maximum value of this z becomes the optimum solution. That maximum value is obtained for some values of x1 and x2, isn't it? For instance, if I get x1 as 2 and x2 as 3, let us say. Now this is not the answer, I'm just taking some random values. So if x1 is taken as 2 and x2 is taken as 3, z will give us some value, isn't it? Now this 2 and 3 can be the optimum solution, isn't it? It can be the feasible solution. It has to first of all lie to the feasible solution. So you got to know first of all what a feasible solution is, isn't it? So if I solve these three inequations, all the values of x1 and x2, which will satisfy all the three inequations at a time, all those values will be called as the feasible solution, isn't it? You have to watch my previous lectures to understand these basic concepts. So when I say feasible solution, it basically means those values of x1 and x2 which will satisfy the three subjective functions, the values of x1 and x2, which will satisfy the three subjective functions. Out of these values, now these are called as a feasible solution. Out of these values, the values which will give us the optimum solution, isn't it? The maximum value for z, 4x1 plus 10x2, that particular value of x1 and x2 will be called as the optimum solution. So there is a feasible solution, then there is an optimum solution. Feasible solution, all values of x1 and x2 which can satisfy all the subjective functions, and from those values of x1 and x2, which one will give us the optimum solution, isn't it? The maximum value, because the problem is asked for maximizing, isn't it? So out of those feasible solutions, that set of values which can give us the maximum value, that set of values will be called as the optimum solution, isn't it? So now what I can do over here is I can make the simplex table and get the answers. Now what important, as I said, in this problem you want to watch for is, sometimes, now most of the questions you will always get one optimum solution. That means there will be only one values of x1 and x2, which are the decision variables, which will give us the optimum solution. Listen to this statement very carefully. Most of the times whenever you are solving a question, most of the times you will get only one set of values of the decision variables x1 and x2, which will give us the optimum solution. So that means the solution is unique. We say that the solution is unique. But students, there might be a case when out of the feasible solution, 2 points or maybe more, 2 points or maybe more points can go and give us the optimum solution. For instance, if I write, let us say x plus y is my optimum solution, is my objective function, z is equal to x plus y is my objective function. Now my feasible solutions are, let us say 1, 4, 2, 3, I can write 3, 2, 4, 1. These are all my feasible solutions. That means I had the objective function as z is equal to x plus y, and these were all my feasible solutions. So if you take 1, 4 and put up in this equation, the value will come 5, z comes 5. So for 1, 4 the value is coming 5. For 2, 3 also the value will come 5. For 3, 2 also the value comes 5. For 4, 1 also the value comes 5. That means it is quite possible that if you have multiple feasible solutions can give us the optimum solution. That is quite possible, and that is what is going to happen here. There will be 2 points which will give us the optimum solution, the maximum solution. So you have to keep on cross-checking whether there will be a unique solution or there will be 2 points or more points which can satisfy the given objective function. Means it can give us the maximum value. Now how do I check whether a given problem will have a unique solution or it can have multiple solutions? Now student, that is what you want to understand here. That is what the key concept is here. So I'm going to rub this out. Okay, so you want to watch closely when you take a look at this problem. If you observe the objective function, it is 4x1 plus 10x2, isn't it? 4x1 plus 10x2. So the coefficient of x1 is 4 and the coefficient of x2 is 10, isn't it? Now if you observe this subjective function, which is 2x1 plus 5x2 less than or equal to 20. Now if I take this subjective function and I multiply this with 2, let us multiply this subjective function with 2 on both the sides. So I'll be getting here 4x1 plus 10x2, isn't it? And less than or equal to, I get 40. Now look at this subjective function. The coefficient of x1 and x2 is 4 and 10. So this is a clear indication that the given linear programming problem will have two or more than 2 feasible solutions satisfying the optimum solution. Listen to the statement very carefully. when you observe that this particular objective function is 4x1 plus 10x2 and there is one subjective function where the coefficients of x1 and x2 are exactly same as your objective function. So the objective function and the subjective function, the coefficients of the decision variables will be same. Whenever this thing happens, be very sure that there will be multiple points which will be giving the optimum solution. Multiple points which will be giving the optimum solution. For instance, I'm going to show this with the help of a diagram. Observe carefully. Suppose if I take x-axis and y-axis, and if I draw a diagram something like this. Okay, so that's the first line. Let us say I'm going to call it as L1. Then there is a second line. I'm going to call it as L2, and that's the third line. I'm going to call it as L3. Now, let us say this is the feasible solution. Okay, this is the graphical approach of solving a given linear programming problem. Now, this you have already learned in your 12th standards, isn't it? So, you have already seen how the diagram looks like and what the way of graphical solution is. So you already know what the graphical solution for a given linear programming problem can be. Now if you observe, let us call this point as O, the origin. This point is A. I'm going to call this intersection point as B. The next intersection point as C. And then I have say point D. Now if you observe this feasible solution, O, A, B, C, D. These are the 4 points usually. Most of the times the optimum solution will always lie on the corners of the feasible solution. Listen to the statement again one more time. The optimum solution will always lie on the corners of the feasible solution. That means point O can give us the maximum solution, point A, point B, point C, point D. So out of these 4-5 points, 1 point can give us the optimum solution. Now sometimes what happens is, out of these 4-5 points that I have over here, now usually 0 will not give us the optimum solution. One of the points A, B, C, D will give us the optimum solution. So at that time when only 1 point can give us the optimum solution, then we say the given linear programming problem has a unique solution. It will have a unique solution. Only 1 point satisfies the maximum value. Only 1 point gives us the maximum value for the given objective function. But sometimes what might happen is there might be 2 or more points which can give us the optimum solution, which can give us the same value. For instance, if I take this point B and C, point B and C both are giving me the optimum solution. Let's for instance, for an example, we will take here that point B and point C, both of them are giving us the optimum solution. Now when point B and C both are giving the optimum solution, we will say that the given linear programming problem has infinite solutions. Now how do I get this? Now observe this statement very carefully one more time. If there are 2 or more points which are going to give us the optimum solution, so here I am going to take that B and C are the points which are going to give us the optimum solution. So if there are 2 points giving us the optimum solution, then the given linear programming problem will have infinite solutions. That means when you join the points B and C with a straight line, every single point between B and C will give us the optimum solution. So that's why I am saying that the given linear programming problem has infinite solutions. Every point between B and C will give us the optimum solution. So we say that the given LPP problem has infinite solutions. So it's very simple. So if you get 2 or more points which are going to give us the optimum solution, then we say that the given linear programming problem has infinite solution. But how do I come to know when I'm doing an analytical solution? That means when I'm doing the simplex method. At that time we don't have this particular diagram, isn't it? We don't make diagrams for simplex method. So at that time, how do I judge whether I'll be getting infinite solution? So that's an easy way. You observe the objective function and the subjective function. If the coefficients of the decision variables, which are x1 and x2 in this case, in the objective function, and the coefficients of the decision variables in the subjective function, at least one of them, if the coefficients are equal, if the coefficients are same for the decision variables, then you be very sure that the given LPB problem will have infinite solutions. So let's take this statement one more time. If you have the coefficients of the decision variables in the objective function and in the subjective function, at least one of the constants in the subjective functions, if the coefficients of the decision variables are same, then you be very sure that the given linear programming problem will definitely have infinite solutions. So students, do not stop when you get the answer for simplex method over here. When you do this question by simplex method, make sure that you are going to solve this problem using the simplex method. So once you reach at the optimum solution, once you have got all the values, go one more step ahead, go for one more table ahead. So as soon as you go for one more simplex table ahead, you will again end up with the same answer of the objective function. So when this happens, that means you get two different points for which you will be getting the optimum solution. So any values, when you join those 2 points with a straight line, then any point lying between the 2 points will definitely give us the exact same answer for the given objective function, and hence we say that the given linear programming problem has infinite solution. So that was the first typical type of question that you want to understand. Now let's discuss the second question also very quickly. Now if you observe the second question, maximize z is equal to 107x1 plus x2 plus 2x3. Three decision variables are involved. In the objective function 107x1 plus x2 plus 2x3, there are three decision variables involved, subject to, if you observe now, x1, x2, x3, and there is x4 also, and it's an equality constraint, isn't it? It's not an inequality constant, it's an equality constraint. And the other two inequations have only three decision variables, x1, x2, x3, x1, x2, x3. So what is the difference in this question? Over here, you want to understand that the objective function and the subjective function has only three variables, x1, x2 and x3. The equality constraint has this additional variable x4. It is nothing but your slack variable. Your actual question was 14x1 plus x2 minus 6x3 less than or equal to 7. Now you have to take one very important care over here is, I am going to write this equation 14x1 plus x2 minus 6x3 plus 3x4 is equal to 7. I'm going to divide this entire equation by 3, because if you remember, the coefficient of the slack variable is always 1. You remember the slack variables, isn't it? The coefficient of the slack variable is always 1. So I'm going to divide this equation by 3. So I get divide throughout by 3. So I get 14 upon 3 x1 plus 1 upon 3 x2 minus 6 divided by 3. I will be getting 2 x3 plus 3 times of x4 divided by 3, so 3 and 3 cancels, and x4 I am going to write it as s1 is equal to 7, or I can go ahead and write s1 plus 0 s2 plus 0 s3 is equal to 7. So that's what the different concept of this particular question is. You already have one slack variable given into the question, ready-made, isn't it? So this is an equality constraint. There are only three variables involved. So the fourth variable here, x4, is actually your slack variable. So I'm going to rename it with what? I have renamed it with s1. Now when you come to the second inequation, it is 16x1 plus 1 upon 2x2 minus of 6x3 plus 0s1 plus s2 plus 0s3 is equal to 5, and the third in equation becomes 3x1 minus of x2 minus of x3 plus 0s1 plus 0s2 plus s3 equal to 0. So that's my 3 inequations transformed into equations. So what change you observed in this question was there was already an equality constraint involved in this particular question. So what I did is the fourth variable I have taken it as the slack variable. Now very important, you want to remember that the slack variable will have coefficient equal to how much? The coefficient of the slack variable is always 1. So that is why I first divided this entire equation by 3, and then I have proceeded with the same concept that we have learned in the previous lectures. Now rest of the problem now becomes exactly similar that you have seen in the previous lectures. You again make a simplex table and keep on solving the question. So here again, if you observe, the coefficients of x1, x2 and x3 do not match with any of the subjective functions, isn't it? None of the coefficients of the decision variables are matching the coefficients of the decision variables in the subjective function. So this particular linear programming problem will have a unique solution. So these were the two different types of questions you want to remember. I strongly recommend you that you solve these two questions using the simplex method. And students, if there is any doubts in these two questions, make sure to give a comment into the comment section over there. I will be more than happy to help you out. So students, I'm going to leave you here with this particular topic, the simplex method. We have seen all the concepts which were required to understand this entire chapter. Make sure that you watch these videos continuously, regularly, again and again if you want, and understand the topic very thoroughly. So students, thank you so much for watching. You have a great day ahead.